Hi, everybody. Today, we're going to get into kind of our first day of affecting a graph. So what you'll see on the handout for today on our lesson page and what you'll see on the screen right now is we're going to jump into stretching a function. And the way that we're going to do that today is we're going to actually work through a little bit of an activity. Now, that activity is going to require us using Desmos. And so today may be a little bit of a difficult aspect. If we are watching this video on one device and we have one device only, then hopping back and forth may be a little complex. For instance, if it was your phone. But you might be pretty talented at doing that, at flipping back and forth between watching this video and playing with Desmos. And if that's the case, outstanding. If you happen to be watching this and you have access to another device, then it may make your time a little bit easier to be watching the video maybe on your phone and then playing around with Desmos on a laptop, something like that. Two devices are not needed, but they may make your life a little bit easier. Okay, what we're going to work on is we're going to work through filling in this handout, but I want to talk a little bit about what you see on this handout. The first thing that you see in the top left corner, and I'm just going to circle that in blue, is the way that we're going to enter in the function. And what we want to enter in is f of x equals sine x. And you should be good to recognize your good old trig. There's our sine. What we're going to actually do is produce a trig curve. So yes, we are going to be punching in one of our trig ratios and producing a function from that. The second part that I'm just going to circle in red, that's going to be some settings that we're going to want to put in our graph settings to make sure that we can all kind of get a useful picture. Just a way to kind of manipulate a little bit. I'm going to highlight a couple things here. We want to make sure that we're good on our scales, so we're going to make our x-axis from negative 450 to 450. We're going to make our y-scale from negative 1.5 to 1.5. I'm going to highlight in green. We're going to want to make it in projector mode just to make our graph a little bit thicker. And then the part that we may miss is down at the bottom. We need to make sure that our graph is being determined by degrees. So what we're going to do is we're going to punch all of that stuff into Desmos, and I'm going to lead you through a little bit with our entire goal of filling in the bottom. So let's take a peek at it. So I've just kind of zoomed in on the bottom a little bit, and let's just take a look at that instruction. So what you see on the bottom is our instruction to go through and label the max and min values and zeros. And we're going to call those our key points on the graph. So the job is to fill in all of your maximums, your minimums, and your zeros. So you'll see me kind of just highlight where we get to the very top of the graph, where we get to the bottom of the graph, and then all of our x-intercepts, because x-intercepts are another name for zeros. So all of those spots that I've highlighted in purple, you'll find that they're blank on your handout. What we want to do is we want to find the coordinates of those points. Okay, that's what we're going to do to fill in. So I just want to come back up and make sure that we are good with what we need to work on. We're going to enter in our trig function, and we're going to make sure that we're in projector mode with a scale and measuring in degrees. Okay, what I'm going to do is I'm going to hop onto Desmos here so that we can just kind of walk through this process and we'll get comfortable using Desmos again. Okay, so what you should see on your screen now is we have Desmos up. And what I'm going to start with is my graph settings. So if I go and I pull that up, I'm going to change to projector mode. It's going to make everything just a little bit thicker. On my x-axis, I'm going to enter in a negative 450, and you'll see your scale, jump pretty quickly. Then I'm going to select and go up to positive 450. On my y-axis, I'm going to go from a negative 1.5, and you'll notice on Desmos, an addition subtraction sign would work the same as a positive or a negative. Okay, I have my scales correct, and the only thing I need to remember is that I need to switch to degrees. There we go. Okay, now I'm going to select into my graph, that bar, my function menu, and now I'm going to enter in my notation. So I need my f of x, which I can just replace as y if I like, my y equals, but it works really well if we can punch in our f of x. So I'm going to switch over to my keyboard and enter in my f, and now I can go back to my numbers, punch in my x. That's going to equal, now I need to enter in my trig function. Well, if you take a look at the bottom right on your keyboard, you'll see a function button. And if I select that function button, another menu pops up. And you'll notice that I have a bunch of tabs. My first tab or default tab should be trig. And you'll notice in the top left corner, there's your sine function. So if we enter in our sine, and now we can put in our variable for x, we'll close the bracket just to make it look nice and pretty. And there is your function. So I'm going to get rid of my keyboard just so we can see the full function. Now, what your job to do is to go in and find all of the maximums, the minimums, and your zeros on that curve. So if we want to just select on that curve, and if you just tap on one of those key points, you're going to notice that the coordinates of that point pop up. So your job, let's take, 30 seconds and work our way through and try to now select all of those zeros and so on and write down all the coordinates for those key points. Okay, I want you to pause the video now, work your way through finding all those points and labeling them on our lesson page. Okay, we should be done, and now we're just going to do a little confirmation on our handout. So what we should see should match up with what we have on our page. So I just want you to scan across really quickly and make sure that we match up. We're going to want to make a note of those key points. So if we were just to examine, I notice that one of my key points is at 0, 0, the origin. My next one is at 90 and 1. My next one's at 180 and 0. My next one's at 270 and -1. My next one's at 360 and 0. And so maybe we're just making sense of a little mental note of those key points. We have them on the page so that we don't have to memorize them. Same thing going backwards, -90, -1. There's all of our key points. Okay, what we're going to do now is we're going to start playing around with Desmos, and we're going to start changing that graph. So let's start affecting the graph and seeing the outcome. So at the bottom of that page, I'd like you to fill in that blank. Now again, we're not just blindly copying. What we're going to do is we're going to use Desmos to start changing the graph. And it's important for us to note that changes to a function are called transformations. Transformations is a generic term that simply means a change to our graph. It doesn't tell us what type of change. That is our generic term, and today we're examining one of those transformations. Okay, what we are going to do is we're now going to zero in on what y equals 2f of x looks like, what y equals 5f of x looks like, and what y equals 1/4 f of x looks like. So what we're going to do is we're going to go ahead and use Desmos to build those other three graphs. Now, I've just made a little note at the bottom. We're going to have to change our scale sometimes to be able to see the full function. that one of our changes may end up making that graph so much bigger that it doesn't show up on our screen the same way. And so maybe we zoom in, zoom out, do whatever we need to. However, that last part, we have on the front page our generic scales, what we set our X and Y scales to. So if at any time you want to just reset and zooming in and out with your fingers doesn't allow you to get back to that picture you like, then just feel free to use those scales at any time to reset your picture and start all over again. Okay, so what we want to do is we want to play around with Desmos and we want to start doing the purple, the red, or the green. We want to see what happens to our graph when we do that. So I'm going to ask you, hop onto Desmos. Punch in the equations to those graphs, and again, make sure that your first one is called f of x. And see what the effect of multiplying f of x by 2, for instance, that purple graph, would look like. Multiplying it by 5, the red graph. Multiplying by 1/4, the green graph. You play around with it and even start just changing what number you want to multiply by out in front. And let's see the effect on the graph. Okay, play around with Desmos. Pause the video now. Okay, we're back. So hopefully you had a chance to kind of play around with it. I'm going to hop in just because I don't think we're pros at Desmos yet. Okay, so what we see on the screen, there is our basic sine curve. Now, if we wrote that in as y equals, that's going to cause us some problems. Yes, we get our function that way, but it won't allow us to examine our function notation. So, as I said, what we want is we want f of x. And notice we get our exact same picture because we know we can always replace our y with f of x. Okay, what I'm going to do now is I'm going to keep that base graph on, and I'm going to enter in that first equation. So now I'm going to punch in y equals 2. And then I got to switch. There's my f of x. And notice I get that blue graph pop up on my screen. I'm going to get rid of my keyboard so I can kind of see. Now, I'm going to use my maximum, my zeros, my minimums, those key points that we labeled, to try to figure out what happened to the graph. The problem is the graph was made so big, it's off my picture. So I can zoom with my fingers and adjust that, or I can go up and I can use my graph settings. By me punching in that 2, maybe I start to just examine what happened. Well, if I click on my red graph at one of my key points, then I see the location of all of my maximum points. And I see 2 of them that I've labeled on my picture, on my handout. But since I changed the scales, I can now see I've got more maximum points. Well, now I want to see, well, what happens on my blue graph? And so when I select my blue graph and I click on that key point, I notice that that key point happens at the same x value, but now happens at a different y value. And so on and so on. I look at the bottom, my minimums on my red graph, and I look at the minimums on my blue graph. And I'm starting to try to see, well, what happened to that picture? And I'm trying to come up with a conjecture, a hypothesis. Well, maybe I struggle to see that, or maybe I think I've got a pattern. Okay, now what I'm going to do is I'm going to change my blue graph. So if I select in on my function menu, I need to pull up my keyboard because I'm going to get rid of that 2. Hey, look, my other graph, well, maybe my blue graph's just lying exactly on top of my red graph because they are the same graphs. But now I put in my 5. Whoa. I see the effect of that. Well, I now need to shrink that down even more to see what's on my picture. Yikes, that's a pretty cool pattern. Well, maybe one of the other things I notice is my zeros haven't changed. Notice all of the zeros of my blue graph and the zeros on my red graph are still the same. That by me putting a 5 out in front, or a 2, or a 3, it doesn't change the zeros. My red graph is my original graph. My blue graph is my transformed graph. The only thing that seems to be changing are my maximums and my minimums, and they seem to be getting higher and lower. They still occur at the same spot, but they just lay in different positions. Okay, I think what I can see is every time I put a number out in front, attached by multiply, my graph gets steeper. Okay, so I'm starting to come up with a conjecture that I think my graph gets steeper. Okay, I'm going to go back and just put on my original scale, because I've done so much shrinking and stretching that the original picture that I got really used to kind of went away. Okay, I'm going to get rid of graph 2, just so you can still see that graph 1, my original sine curve, it's still there. It was just hidden. Now I'm going to enter in that last graph, the green one. Y equals, and I needed 1/4. Now, you could change your 1/4 into a decimal because it is exact, but I would just stress, like, punch in 1/4. We've got 1/4, and now we need f of x, and something different might have happened. Or at least it looks different originally. Notice my x-intercepts are still the same. The red curve and the green curve cross the x-axis at the same points. So by me putting a 1/4 out in front, I did change my red graph into the green graph, but I didn't affect the x-intercepts. I seem to have affected where the maximum and where the minimum occurs. My maximum on my original red graph, one of them happened at 90 and 1. Now, this maximum seems to occur at 90 and 0.25. Well, maybe we're starting to see a pattern then. This minimum on my red graph occurred at 270 and had a value of -1. Now, that minimum value still occurs at 270, but has a minimum of -0.25. I think we may be able to see a pattern. I think that we're going to struggle with the language to use, and that's where I'm here to help you out. So what I want to do is I want to jump onto our next page and try to sum up maybe what we saw. Okay, let's turn over the page. So what we have at the top of that next page just asks a couple questions for you to think about. So the first question to think about is, what is happening to the y values of the key points? And I hope that we can notice that as we've been working our way through, the y values are changing. We had a maximum of 1 on our base graph. That then got changed to a maximum of 2, to a maximum of 5, to a maximum of 0.25. The y values were changing on that graph. What happened to the x values of the key points? They were not changing. And you may say, like, they're staying the same, but they were not changing at all. So the conclusion we have to draw then is When I multiply a number and put that number outside my function, so I multiply by a 2 or a 5 or a 1/4, outside f of x, my y values changed, but my x values did not. So let's make a general conclusion then. And again, I'm going to help you out with the wording. That based on these transformations, what conclusions may we draw about how the value of a, and I want you to notice that a refers to that a in our graph, the value that is attached to f of x by multiply. What could we now say? Well, we could say that the graph is, and if since we're affecting the y values only and not the x's, then if we think about the direction of the y values, those are our vertical coordinates. We could say that the graph is vertically. And what ended up happening in that case? We were stretching the graph. So we could say that the graph is vertically stretched. Now, if we examine what happened in that last one where we put the 1/4 on, we might struggle to want to use the word stretch for that. It is a stretch, but a word that might seem a little more to make sense with the shape of the graph might be a word like compressed. By us attaching a number outside that f of x by multiply, seem to stretch our graph or compress it, however you may choose to think about it. Okay, next question. Are there any other interesting findings? And yes, I understand that interesting might not be the word you would use. But if I can just get you to maybe draw your attention that the x-intercepts of our sine curve didn't change. That as we multiplied our function by a different value, we still kept crossing the x-axis in the same spot. So the graph became taller, it became shorter. You could argue it became steeper or it became flatter, but the x-intercepts never changed. And there's a key term for that. That when we have points that do not change based on a transformation, they're referred to as invariant. My x-intercepts never moved. Okay, that's us kind of putting together what we saw as a picture, playing around with Desmos, and maybe adding in some terminology. I helped us through maybe how we could examine some of those questions and maybe sum them up with some new vocabulary. Okay, what I want you to do is to now work your way through problem 2. We're going to reset the graph, reset the scales, and let's play around with Desmos to affect maybe something different. So we now have a bunch of new functions that we're going to deal with. So as I said, reset your scales. Let's go back to the original graph. But now, let's multiply the inside by 2 and see what happens there. Let's multiply the inside by 5 and see what happens there. Let's multiply the inside by 1/4 and see what happens. Notice the location of that multiplication changed. Last time we were multiplying outside the f. This time, we're going to multiply inside the f. Okay, let's do the same thing on Desmos. Go as fast as you can go. Feel free to use other numbers to plug in there after you've dealt with those 3 to try to be able to put together an idea of what is happening to your graph as we take that action. Okay, so we're hopping back onto Desmos and we're going to end up punching our stuff through. What I want you to do is I want you to pause the video now, play around with Desmos, and we'll see if we can find our pattern. Okay, pause it now. Okay, we're back. So I'm going to jump in and just punch in a couple of these functions. So let's see what we get if we have y equals f of now 2x. Okay, that became just one big mess. So my red curve is my original sine curve. My blue curve is my changed curve. So to try to be able to see what's happening to that graph, it might be tough unless I draw up my key points. So on my red graph, I'm going to just look at my key points. So that 91. Okay, well, where's my other key points? I noticed something different happened on this graph because that maximum point isn't above or below it. It's now been moved to the side. So if I click on this maximum, well, I have a location at 45, 1. Or if I click on this one, I have a location at like 225, 1. So like maybe the red maximum got moved to one of those spots. Okay, I don't feel like looking at that portion is enough to make me feel confident to say like, yeah, I see what's happening. I see the pattern. Okay, I'm going to get rid of those maximums. And now if I look at my zeros, well, I noticed that my zeros changed. My x-intercepts have changed. Well, I had this x-intercept that was at 0, 0, and that seems to match up with my blue. However, this x-intercept that was on my original red curve at 180, it's not at 180 anymore. So I have this x-intercept on my blue graph, which is at 90, or this x-intercept on my blue graph, which is at 270. Okay, well, where did my red 180 get changed to? Did it get changed to the 90 or did it get changed to the 270? Okay, that can be tough to see. I'm going to argue that if we started to look at all of those together, my red was at 90, it got moved to either 225 or 45. Well, then that means that my 180 had to get moved to 270 or 90. We might start to see something that makes this a little more predictable. And if I was to take a look at my minimum on my red graph, my 270, and then I look at this minimum, 135, I think I might see a pattern. It looks like all of my blue points, the important ones, I'm going to get rid of this one and I'm going to get rid of this one. They've all become half of what they used to be. So my old maximum on my curve used to take place at 90. And it seems like my new maximum takes place at 45. My old 0 used to take place at 180. My new 0 takes place at 90. My old 0 used to take place at 270. My new minimum takes place at 135. So it's looking like all my x coordinates became half of what they used to be. Okay, let me play around with my blue graph now and see, is that true all the time? So I'm going to now change that 2x into the next graph. Oh my goodness, 5x. Now I just have a blue curve everywhere. Well, I'm going to zero in. So I'm going to zoom in a little bit. If I can get to the point, there we go. Where if I zero in on that maximum, it happens at 90 and 1. There was my original one. Well, putting that 5 out in front, maybe got me to 18.1. At the very least, we might see a pattern to it. If I now zoom out, and I've got all these curves so much, that maybe at the very least we can see that that nice smooth red curve that seems to repeat over and over again became this blue curve that's repeating all the time. Like for instance, if I was to highlight on my red curve, up, then down, then up. That same pattern seems to repeat, except in blue, it repeats 1. So much more often. Okay, you keep playing around with the rest of Desmos, enter in your 1/4 x, and we can see how things can kind of play out a little bit. When we're done, we're going to go through and we're going to sum it up. So I want you to pause it now and play around with Desmos. Okay, we're back. So let's jump into kind of that next bottom section on your page. Okay, so what we now have is kind of the same questions. What is happening to the y values of the key points of f of x? And we should notice, oops, that's my highlighter. We should notice that they are not changing. There is no change. My maximum values are still happening at 1. My minimums are still happening at -1. There was no change. However, what's happening to the x values? They're changing now. Where my maximum occurs changes. Where my minimum occurs changes, and so on. Okay, could we draw a conclusion on this one? And again, let's draw to our attention the effect of P. And when I look at the location of P, it's on the inside of my f of x, and it's attached to my x by multiply. So what could I say on that? Well, I noticed that the graph, my one that keeps changing, is now horizontally stretched or compressed. My y values didn't change, but my x values changed. Well, x values are horizontal coordinates, so my change to my graph must be horizontal. Now, I've put down explicitly on the next question, did we have any invariant points for that one? And if you hop back onto Desmos, we might be able to recognize that, in this case, my y-intercept is invariant. It did not change. Okay, I put down on the bottom a couple little stars there, that if you want to, you could go back and deal with this exact same process, but change your graph. That rather than use a sine curve, well, you could use a cos curve. And then you can examine the effect of your p value, and notice we're just calling it p, the value that's attached on the inside by multiply, to maybe see what happens to your cos curve as we put in different values of p. That might help you out to see a pattern if we're struggling to see one. Okay, all of this kind of play time is really important for us. It allows us to see some patterns to some things. What I want to do, though, is I kind of want to organize it a little bit. But in order to do that, I think what we have to do is we have to examine both of these effects together. Okay, so if we flip over the page, then what we're going to see at the top of the next page, problem 3 or activity 3, is going to be us having to reset again back to our graph settings. So you have your scale up there. However, what you're going to notice is I've changed your scale on you again. Down here is the more important adjustment. Notice that what we're going to do is we're going to change our x-axis back to its original, but our y-axis, we're going to want to put from -5 to 5. That's going to allow us to kind of see some of the effects. We've noticed that a few times we've been stretching the graph too far vertically and it's gotten off of our screen. So if we adjust it to that value, then I think we should be good. Take a look at the top right corner of your page. Now what we're going to do is we're going to graph y equals a f of p x. Now you might be looking at that and you're saying like, so we just like punch in a f, yep, we are going to type that exact same thing in. What we're going to do is we're going to add what are called sliders in Desmos. Before you do that on Desmos, I just want you to take a look at what your function menu is going to look like. That when you punch in y equals a f of p of x, you're going to now create or be asked to add sliders. And we're going to click all. And when we do that, you're going to now get a slider for A and a slider for P. So what I want you to do is to go through and punch that into Desmos. That's going to allow us to kind of play with Desmos a little bit. Okay, go ahead, punch that into Desmos, pause it now, and when we come back, I'm going to be back into Desmos. Okay, and so you should be back. If we had any difficulty, no worries. You'll see that I've entered in my y equals a f of px. And there's my request underneath. Desmos is asking me if I want to add my sliders, and I'm going to select all. When that happens, I get my 2 sliders in, and you'll notice that I have a scale for each slider. Now, what I want to do is I want to change those scales. So, where I see my -10, I'm going to ask you to click on that, and we're going to change that to 0 up to 10, and you'll see that that matches with your handout. And we're going to do the same thing on our P slider. We would like to go from 0 up to 10. And now if I just click on my graph, I can get out of my function menu. What sliders allow you to do is you can click, and I'm going to click on my A slider, and I can now slide that to different values. So you'll notice that there is me with an A value of, and I'm going to do my best to get to stay on it. I have horrible nerves. There we go. There is my A value of 1. And notice I match up. As I start to make my A value bigger, I see what's happening to my graph. So sliders become a really fast way to see repeated substitutions of values. So rather than us doing subbing in a 2 and then subbing in a 5 and then subbing in a 1/4 and so on, we can use sliders to now, what happens if we have a 5? What happens if I have a 3? What happens if I have a 10? And so on and so on. We can see the effect of changing A. Well, if I reset that to a 1, and you can just click on A and do it, then maybe I take a look at what's happening with P. And notice as I change P, I can see what's happening to my graph. I'm taking my red graph and I'm changing it to create the blue one. So maybe through that act of using sliders, we can actually get a little bit of a better understanding of what's happening as we start to put numbers in place of where the A or the P are. Now, I put right below that about finding it a little bit easier to see the effect of an A value or a P value by changing your slider. Like it's really tough for us to see and slide to decimal amounts. We can see the effect, but we have to be so fine because 0 to 1 on there is such a small distance. That maybe what I do is I click on, and I'm going to change that to a 2, and click on and change that to a 2. that now, if I reset that to 1, I don't have to be so fine. I need to get that back to 1. So I just click on it and type in my 1 maybe. Now I can use my slider on P, and I get a much better understanding of what happens as my value out in front is less than 1. So like if it's a fraction, I get a number bigger than 1, and I see what happens if I have a number bigger than 1. If I reset that back to 1, and I'll do my best to get to 1, then I can do the same thing with my A value. I have a value bigger than 1. I see what happens to it. I now have a value less than 1. I see what happens to it. So sometimes using sliders, but adjusting your scale on it will allow you to see a pattern a little bit better. Okay, I want you to play around with Desmos under that context. And when we think we've got something, then we're going to jump together and we're going to summarize at the bottom of that page. Okay, when you come back, we're going to be on our summary. Okay, we're back, and what I want you to do is just take a peek at what I've put down for our summary so far, because we're going to actually get down quite a few notes on the bottom of that page. The first thing, notice that I've put down a generic function for us right now. So I have y equals a f of px. I've just written down my a and my p in different colors, so they really pop for us, that those are the differences to f of x. Now, here's a way that we can sum up what's happened because of the a value. That a value exists outside the function. We can see its position. It is outside f of x. It's outside the brackets. And if we think about outside f of x, then we're affecting the outside of the function. We're affecting the outcome of the function. That means we're affecting the output. Now, that's not an idea that we put into our head automatically, but what we should have noticed through playing around with Desmos is when I change my a value, I'm changing my y values. Now, we just saw that through practice, but now we want to connect the idea that my y value is my output. We know that from a function, right? You pick your x, you sub it in, it spits out its output, it spits out its y value. And if I was to ask you, well, what direction do your y values run? Well, our y values are our vertical coordinate. And so we should be able to then make a bit of a shortcut and say that my a value affected my output, which affected my y values, which affected the graph vertically. We should then be able to go, oh, well, therefore my a affects the graph vertically. Okay, let's start to take a look at our P then and try to see if we can make a comparable statement. Where is our P value? We notice that it's written inside the function. You notice where it is in our equation. It's on the inside of f. It's with the x. So P is on the inside. It's with the x. So if you notice within function notation, you should be subbing a P of x back into f wherever you see the variable. That means you're subbing it into the function. That means it's your input. And if it is the input, then those are the x values. And if I was to ask you, what direction do x values run? That would be horizontal. So if P is on the inside of the function, inside is my input, then the inputs are the x values run horizontal. Sum it all up, P affects the graph horizontally. Nice. We are starting to drive this outside versus inside, vertical versus horizontal aspect. Okay, what I want to do is I want to sum up a couple other things and maybe introduce some terminology, some way that we're going to speak about this. What we're going to do is we're going to put a little heading down, because what we're going to do is we're going to zero in on just the A value. How would you describe the change to the graph as an A value? Well, we would describe that as a vertical stretch. We are stretching our graph vertically because of that A value. And we would describe it as by a factor of A, like whatever number A would be. So if you notice, on Desmos, if we switched our A value into a 2, then all of our Y values were doubled. We vertically stretched our graph by a factor of 2. When we added in a 5, I shouldn't say add, because it's attached by multiply. When we changed our A to a 5, now we saw that our graph became even steeper. So it was vertically stretched by a factor of 5. Our key points now had a Y value that was 5 times what it used to be. Okay, so we need to write down some stuff explicitly, because within the vertical stretch by a factor of A, different things happened. So first off, if we can get down that if my A value was a certain type of number, that is, it was a number bigger than 1, then I found that my graph is steeper. So it became steeper. That notice when we had a 2 out in front or a 5 out in front, and especially when you were able to work with the slider, you notice that anytime that A value was greater than 1, it's like we were stretching that graph away from the x-axis. Anything on the x-axis stayed the same, but our graph became steeper. That then we also noticed that if we had a different A value, an A value that was less than 1. Now, I need to be very clear that we need to add in some notation on that statement, because A being less than 1 also allows us to have an A value that's negative, and we were not even looking at A values being negative, only positive. So what we're going to do is we're going to put vertical lines on both sides of A. What that means is the absolute value of A. And that's kind of a formal way of us just saying, who cares about the sign of A? The number has to be less than 1. So if the number we put out in front, the A value, was less than 1, then we found that our graph became flatter. Okay, now let's jump into our p-value. So we noticed the same thing, that within our p-value, we had a horizontal stretch. That p-value was on the inside's the input, inside horizontal. So we had a horizontal stretch by a factor, and this is going to look a little weird, of 1 over p. Now, if you notice that when we had a p-value of 2, everything on my graph became horizontally half of what it used to be. When we made a p-value of 5, it became 1/5. Remember all the times that our trig curve, our sine curve kept repeating? Okay, so what ended up happening then? Well, within that context, if my p-value was greater than 1, so my p was 2 or 5, look where p is up in our original, then that means the horizontal stretch factor would be like 1 over 2 or 1 over 5. That means all my x's became a half of what they were, or a fifth of what they were, or so on and so on. That makes my graph steeper. And for everything that we said before, we need absolute value signs around our p. If p value is less than 1, forget about the sign, but just the number, So like when we put a value of 1/4 out in front, all of a sudden we notice it's like we pulled our graph away from the y-axis. That's because when your p-value was 1/4, then our factor becomes 1/1/4. That actually means it's stretched by a factor of 4. That means all my x's are 4 times what they used to be. We're pulling our graph out really wide. That makes our graph flatter. Okay, if we have down that note, then I think we've got a great summary for us. It doesn't necessarily mean that we know yet how we're going to use this stuff to our benefit, but at least we're taking that first step at examining our transformations. Okay, what I want to do is I want to jump into some practice just so we can see how we can use this stuff. So what we see on our last page then, there's the first problem. We've got describe how the graphs of the following can be obtained from the graph y = f of x. So let's make sure that first off, we're good with our terminology, that we can talk about transformations properly. So let's walk through the first one together. We see that we've got our basic function in our y and f of x. And so we notice what the difference is to it. It's the fact that we've multiplied the f by 1/2. That is, we are multiplying outside the function by 1/2. And given our discussion, we were able to interpret that as a change to the graph. That we know if we are multiplying on the outside of the function, outside is my vertical, and so therefore we're talking about a vertical stretch by a factor of 1/2. If we're multiplying on the outside of the function, then we're affecting the output of the function, and the output is my y value. There we go. There's our terminology. Hopefully not too bad. Okay, I want you to go ahead and try to make the 2 statements that we would have to make for b to interpret the 4 and to interpret the 1/2. Okay, give it a shot. Pause the video now. Okay, we're back. So I'm going to bet and say everybody should have, if I can spell vertical, a vertical stretch, or the graph is vertically stretched by a factor of 4. Okay, that one should have been pretty automatic. However, I'm going to bet and say that we maybe have a bit of an error on the second statement. We interpret the 1/2 and we notice that the 1/2 is on the inside. That 1/2 is being multiplied by x, so we are affecting the x values. X values run horizontal. We know that we have a horizontal stretch. So our graph has been horizontally stretched by a factor of, and my guess would be our mistake in this problem is going to be to write by a factor of 1/2. Okay, remember, we have to be very careful when we're affecting that inside. That my horizontal stretch factor is by a factor of 1/1/2. And therefore, it's affected by a factor of 2. Now, sometimes those stretch factors can be a little difficult to talk about. We can get our factor a little confused. What we like to do is we will add in a statement at the end. That when we're done our formal statement on transformations, which is what you see in red and blue on your screen, we make a little comment about the shape of the graph, because we know when we stretch a graph, we change its shape. And so we've got 2 options. Are we making our graph steeper, or are we making our graph flatter? Let's take a look at question A. I have vertically stretched my graph by a factor of 1/2. Vertically, y values. So all of my y values are 1/2 of what they used to be. That means that on my graph, If I had a point here, it's been stretched to here. If I had a point here, it's been stretched to here. Half the distance to the x-axis. And hopefully then we could maybe see that it's going to look like my graph has been pulled towards the x-axis, and that's going to make my graph flatter. Okay, let's take a look at B. If I have a vertical stretch by a factor of 4, then it's like I'm pulling my graph away from the x-axis. And if I pull it away from the x-axis, that's going to cause my graph to become steeper. Now we take a look at the blue. My blue is a horizontal stretch, so now I'm talking about pulling it away from the y-axis. I'm pulling it away from the y-axis by a factor of 2, so I am doubling all my x values. Well, if I double all my x values and I pull it away from my y-axis, then I'm going to get a flatter graph. We make those little green statements at the end of all of our stretches just to make sure that we can interpret the shape of the graph correctly. Okay, let's jump into the next problem. Now that we have our terminology down, let's take a look at problem 2. So what I've done is I've given you 2 graphs. I've given you your original one in black. That's the thin line, you see. The other line, the thick one, the red line, that's our transformation of the original function. What we've been asked to do is to write the equation of the red function. So we've got a number of ways that we can think about it. The first thing that we should think to is, well, my graph has changed its shape. It's become flatter. Notice I went from my black graph down to my red graph, or out to my red graph. It's become flatter. And so then maybe I start to think about, okay, well, how can I make a graph flatter? Okay, we might already have in mind what we may have done. Okay, I want you to pause it here because I want you to give it a shot and try to see if you can just think of the transformation you would do. Don't worry about writing the equation yet, but think about the transformation you would do to take the black graph to the red graph. Okay, pause it now. Okay, we're back. Hopefully you've got something down, but I wouldn't be overly alarmed if you were looking at it and you weren't sure how to begin. Let's kind of walk through one possible way to view this situation. If I was to take a look at my original black graph, then what I could do is I could try to look for like a point. And maybe like I take a look at this point right here. And we'll identify that, like that's at the location 2, 2. That point on my original graph could have been changed to a point on the red graph, or it was changed to a point on the red graph. That's our transformation. So maybe then I kind of tie in and I say like, well, maybe that blue X got changed to the green X. And I start and I take a look, okay, well, my blue point at 2, 2 got changed to my green point at 2, 1. And so then it starts to maybe look like, okay, well, my y coordinate was made half of what it used to be. So now what I'm going to do is I'm going to try to find a little confirmation to that. So maybe I scan over here and I say, well, there's another point. It would be at 4, 4. And it seems like that point at 4, 4 got changed to down here. That would be at 4, 2. And I get a little confirmation. So one of the ways that I could have stretched my graph to make it flatter, to change my black to the red, is to vertically stretch it by a factor that's less than 1. And it looks, if I look at my y-coordinates, like my y-coordinates are always half of what they were before. And so that's what allows me to then say, well, I think that I have a vertical stretch by a factor of 1/2. There we go. There's me writing the equation, thinking of the transformation of what we did to that picture. Now, I've thought of the transformation. Now it's my job to actually answer the problem, which said to write the equation for the function. Well, that almost becomes the easiest part now. I know to vertically stretch something, I have to multiply the outside of the function by that value. There we go. Okay, if that's not what you had, don't be alarmed. That's one way for us to think about that. What I'm going to do is I'm just going to start off with the same method. I'm just going to change colors so we can see how we match up with our answer. But what if I started off with that same point? That I started off with 2, 2. And now I was looking to see, well, where did that point get transformed to? That what I just did in blue was only one option to see, okay, how was that graph changed vertically? Maybe, though, I took a look at it and I wanted to say, yeah, but I think it got stretched out to here. That is, and I'm just going to get rid of that X again. I'm going to make it pop out a little bit more, maybe. That maybe I thought of it as a horizontal stretch, not a vertical stretch. So that point 2, 2 got stretched out to 4, 2. Okay, now I'm going to try to confirm it, get something else. So maybe I pick 4, 4. The only problem is I notice 4, 4 is kind of a bad option. Yeah, I can anticipate that my red line will go, and therefore maybe it was stretched out the same way. But what I want to try to do is find another point where I can get both points, the original and the transformed point on my graph. So maybe I hop over to the left side. Well, there would be an instance where I was at -1, 1. That seemed to have gotten transformed to -2, 1. My pattern's continuing. Maybe I'm here at -3, 3. That got transformed out to here. That was at -6, 3. And I notice that my pattern continues. So I want us to see that we have a bunch of options. Now, if I viewed it the purple way, then I'm not viewing it as a vertical stretch. I'm viewing it as a horizontal stretch. Now, by what factor? Notice all of my x coordinates became double what they used to be. So, by a factor of 2. Now the biggest one that we've got to make sure that we're good with. To change that into the equation, I'm changing the inside of my function, the x coordinates. So I need to multiply on the inside. If it is a factor of 2, then that means I need to multiply my x's by 1/2. If all my x's are double what they used to be, then I've got to multiply it by 1/2 on the inside. Okay, there we go. 2 possible answers that would get us to the same transformed graph. Nice. Okay, let's jump into the last problems. Okay, I'm going to argue that I think these problems would act a little bit like some problem-solving situations. That is, we haven't spent a whole lot of time solving equations this year yet, and we definitely haven't solved a whole lot of cubic functions if we take a look at the function that's given in the problem. So, for us to be able to work our way through, I think this would fall into the problem-solving category. So since this is the first one that we're going to kind of tackle together, some problem solving stuff, let's play through this first problem together. So give problem 3 a read and unpause it when you're ready to come back. Okay, we're back. So the question said determine the zeros, and we should be good that zeros is another name for x-intercepts. If these transformations of the original function, blah, blah, blah. Okay, so the first thing that we can look at is we could tackle this problem completely algebraically. That is, we have enough background now with what function notation is that we could interpret problem A strictly as an algebraic problem. That notation says go back into F and replace all your x's with 2x. So if we were going to follow that function notation, I'm going to do that in red, then what that becomes for f of x, or I should say, sorry, f of 2x, is replace my x with 2x, replace my x with 2x. Now, what we can do is we can simplify that expression, cube the 2x, so cube the 2, cube the x, and we come in on that red function. Now, the problem asked us to find the zeros, so that means make your function equal to 0. And now what we've built is we've built an equation. And we could go through and solve that equation. So for us, we can say, okay, can I put my variables into one term? No. So then what do I need to do? Well, I really like to factor. I notice that on the left side, I have 2 terms, and both those terms have a common factor of 2x. Well, if I factor out a 2x from the first term, then that's going to leave me with a 4x squared. And if I factor out a 2x from the last term, that leaves me with a 1. We have enough factoring review now that we can see that that inside could factor further. And maybe we want to factor this. We didn't have to. But that might just allow us to see a little more explicitly that we're going to actually have 3 solutions to that equation. Therefore, 2x equals 0. So x must equal 0. 2x plus 1 equals 0, so that means a negative 1/2. Or 2x minus 1 equals 0, a positive 1/2. And so we come in on 3 possible solutions, x equals 0 or plus or minus 1/2. There we go, we are good. You've answered the problem. Determine the zeros of the function if the transformations occurred to that graph. And you have now just come up with what are the zeros of that function. Okay, I'd like to tackle A a different way. Because if I was to work through A, I don't think I would work through that way. That as much as some of us might be more confident in our algebra, I think thinking of this problem graphically might be your easiest way. So what I'm going to do is I'm going to put down a quick set of axes because the question asks me to determine the zeros of the function. So what that might mean is, well, if I could find the zeros of the original function, then I could just do my transformation to it and see the result. Well, in order for that to happen, I do have to deal with a little bit of algebra. I have to find my zeros of my original graph. Okay, you can see what we just did in red. I think we should be able to do the same in blue. So I'm going to ask you to pause the video and find the zeros of our blue function, blue equation. Okay, pause it now. Okay, we're back. So we can't put our x's together into one term. We can go ahead and we can factor. And maybe we can see right there that we're going to get an x value of 0 from the first x or plus or minus 1 from our next factor. So now that I have those x-intercepts, what I can do is I can just plot them on my sketch. So I know that I have an x-intercept at 0, and maybe out here at 1, and down here at -1. Okay, now what I can do is I can take a look at the effect on my function notation, and instead of just thinking of that algebraically, I can interpret that as a transformation. So we've spent time today figuring out, okay, what does multiplying by a 2 on the inside of my function do? Well, if I multiply by 2 on the inside is horizontal, then I'm going to horizontally stretch my graph, and I need to remember, by a factor of 1/2. So that means that all of my x values are going to become half of what they used to be. Well, 0 was always on 0, so to make 0 half the distance to the x is no change, it's invariant. But my 1 would get transformed to 1/2, and my -1 would get transformed to -1/2. All my x's would become half of what they used to be. And notice, we come in on the exact same solution, 0 and plus or minus 1/2 as our new x-intercepts, our new zeros. So, although we may have a tendency to want to use algebra most of the time, and we may be a little more nervous about dealing with constructing pictures, our graphs or sketches, I think the sketch is actually the easiest way to go about doing that, especially if I'm pretty quick to be able to find the x-intercepts or zeros of my original function. So what I'm going to ask you to do is, let's go ahead and let's try to tackle b. Except, let's not deal with b in two different ways. You pick whichever way you would like to tackle b, and let's go through and try that one on our own. Okay, so pause the video now. Okay, we're back. So, since I already did the blue work, then I'm going to go through and I'm going to put on my sketch again. I'm at 0, 1, and -1. Now, I take a look at the changes to my equation, and I just have to interpret those as transformations. So, the first thing I notice, I've got this multiply by 3 on the outside of my function. Well, that's going to be a vertical stretch by a factor of 3. Well, the problem is these points are on my x-axis. And so if I was to vertically stretch those by a factor of 3, they're not going to move. That vertical stretch has no effect on my x-intercepts. They're invariant. So now I can go through and I can interpret, well, what does multiplying by 1/3 on the inside of my function do? Well, the inside is horizontal. So I would have a horizontal stretch, and I need to remember, by a factor of 3. So that means that all of my x values are now going to be triple the distance from the y-axis. They're all going to be 3 times what they used to be. Well, 0, if I make that 3 times what it was, is still 0. But my 1s are going to become triple what they would be. So 1 gets stretched all the way out here, maybe to 3. -1 gets stretched all the way down here to -3. And regardless of the rest of my picture, the question asked me about my zeros. I know my zeros are now going to be at 0 and plus or minus 3. So hopefully we went through and we dealt with that graphically. I think that's going to make your life easier. If you went through and you dealt with it algebraically, I think that becomes pretty ugly, at least for today. Okay. Hopefully us working through some of that practice gave you a little bit of an experience for how we can use this stuff, but it's still just day one of transformations. So for us to begin to build and to start to add in other transformations, I think is going to give us greater context to how we can deal with our graphs. Okay, your job now, jump in and get some practice and make sure we can focus in on being really, really comfortable with dealing with stretches. Okay, best of luck.